All right, we're gonna model springs and we're gonna take a look at a few scenarios. Um, and so it's some spring system with a mass attached to it. And you guys have seen models of this, right? Like real life models. So we don't have to bring it in. So there's a couple of scenarios here. Um, One of them is the spring is free of friction. There's no damping, so it could go on forever potentially. But in a more real life situation, in spring, there's a damping force where it's eventually going to stop. So let's. Oh, and also there's another scenario where the spring is attached to a motor, and the motor has its own system, and so the spring will bounce up and down, and then the motor will start to take over, and then so it's going to eventually follow the motor's um, system. Can you imagine all that? All right, good. So when we model, we're just going to set up our system of differential equation, or not system, but we're going to set up our differential equation. And in these problems, we're usually going to be coming up with some initial conditions as well, so that we can solve for that and then try to figure out how to graph or how the system might look like. And the modeling that we're going to do will mainly stick with um, will mainly be restricted to just second order differential equations with constant coefficients. So there's some information here that helps us set up our differential equation. And I'll just copy and paste all this stuff here. Okay, so we have a spring hanging down and measure the length at rest, and we attach a mass M, and then now the spring gets stretched by some certain amount. And then there's a Hooke's law. This is all just pretty much there to explain how the setup's going to work. Hooke's law says that the force is equal to the opposite direction of the stretching. It's proportional to the stretch, and so F is equal to K times S. Um, so this is going to assume that your equilibrium at rest when you go down, it's positive. It's a positive distance. So um, maybe I should spell it out. Positive. So going down is positive for a spring system, and then going up would be negative in terms of the direction that we're looking at, because it's a length that we're stretching. So aside from that, there's a second law, Newton's second law, that says that the force is equal to mass times acceleration, or mass times gravity, and then um, so that two forces, we can set the two forces equal to each other. And then here it says, suppose a spring is pulled by a distance of x and then released, restoring its force is going to be k times x, the distance that it was pulled, and then plus s. Assuming there's no damping effects on the spring, there's no external forces that would move the spring, the force can be equated by Newton's law. So the gravity or the acceleration, we'll call the second derivative, and that's equal to negative k times x. The bottom line is we get this differential equation. So this is mass times acceleration, or the gravity. Well, the force is, this whole thing is the force, right? Mass times acceleration. And that's equal to this thing, the force, after we pulled and let go. Yeah. And m is your mass. Yeah. So in any case, I'm just curious, or we get down to this differential equation. What's omega? Omega squared. What? K over m? Close. But yeah. So if we take these two, you got m d squared x over dt squared. I guess we could just call that x double prime is equal to k times x. This is mx double prime plus, oh, this is negative, plus kx. Try to figure out what omega squared is. And if you divide both sides by m, you're going to get x double prime plus k over m. X is equal to 0 over m, which is still 0. So omega squared is what? Close. Oh, omega squared, yeah, k over m. But then omega itself is the square root of that. Yeah, you guys are right. And we know that the mass is positive, that the k is positive, so we know that this is going to work. K is a spring constant, they call it. It's from Hooke's law that says that if you have a spring just hanging there and then you attach mass to it and it stretches down, so that amount that it stretches down is that force that's being applied to it. And so for different springs, you'll have different stretching down amounts that you have. So that's called a spring constant. So this is assuming that there's no damping. In real life, there would be damping because spring will eventually, because of the air resistance and stuff like that, it'll eventually stop oscillating. But assuming that there's none of that issue, then it's going to go on forever. That's your simple harmonic motion. Yeah. Pardon me? It's called omega. It's a Greek letter omega, and they use it for what do they use it for in physics? Frequency. Yeah. 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 Because when you take the square root of that, it'll turn out to be omega times the imaginary number, and then we just say it's going to be the sine of omega. Looking down, looking ahead. Okay. So let's do some examples. I don't know. Every time I start an example in the middle of the page, I run out. Maybe we should start a new page. So we're gonna do some light physics here. So here's our first example. We're using pounds here for some reason, and inches and stuff. So um, we have to be able to negotiate the difference between dealing with whatever system this is versus the metric system. It says here, a mass weighing 24 pounds is attached to the end of the spring. It stretches it for 4 inches. Initially, the mass is released from a point 3 inches above the equilibrium position. Find the equation of motion. So there's information here that is going to help us figure out our differential equation, and then there's information here that's going to help us figure out our initial conditions so that we can come up with an IVP, initial value problem. So this stuff over here will help us find an initial condition. And then the other stuff up on top will figure out our differential equation. So since initial conditions I think are a little bit easier, let's figure out our initial conditions. So the mass is released. So when you have when you're pulling the spring in either direction and then you release the mass, um, what can you say about the initial speed that you're giving it? 0. So the initial velocity will be 0. It's like those problems in Calc 2 where you have a ball up, you're on top of a building and then you drop the ball versus you have a ball on top of the building and you throw the ball. So when you throw the ball, it gives an initial velocity. When you drop the ball, the initial velocity is just going to be 0. So that's the same sort of idea here. When you release something versus pushing it, then your initial velocity is going to be 0. So our initial velocity is given by the first derivative, and that's going to be 0. And then now, where did you release it from? The position, you're 3 inches above the equilibrium. And again, the above and below gives a positive and negative, the negative and positive. So above is negative, below is positive. So 3 inches above equilibrium. The initial position is going to be -3. And that's your set of initial conditions that you're going to use for your differential equation. Say it again. If it's above, it's negative. If it's below, it's positive. Pardon me? That would be the position. Because the Hooke's law, when we establish Hooke's law, we're pulling it. When you attach the weight, your spring stretches down, and that they're looking at that as a positive distance. All right, let's figure out now from the other piece of information what our actual differential equation is. Oh, by the way, since we are dealing with pounds, we should also be dealing with feet, I think. So I think instead of 3 inches, um, very good with units here. Instead of 3 inches, we probably convert it into feet. So we could do that now, or we could do that later. But let's 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 think about this in feet and pounds, because the force is going to be Is that force foot-pounds? Something like that. That's in meters. When we're talking about metric system, we're going to talk about kilograms, but well, yeah, unless they give it to us in pounds, then we'll stuck with it in pounds. Yeah, if they gave it to us in pounds, we'll work with pounds because there's equivalent. Um, what? Well, the K will have to be expressed in pounds, and so I think it's in pounds per something. I forgot. Um, so, anyways, we'll do a different example where we're talking about things measured in the metric system. But for now, let's finish this up. 24 pounds. Now, the tricky part about pounds is that we're assuming that um, the mass is not the pounds is actually the weight, and the weight is actually the force. So when you say pounds, you're actually giving the force. So this is not your mass, but mass is, or force is equal to mass times the gravity. So we're going to assume that the gravity is 32 feet per second. Force is equal to mg. G is 32. I guess they use S for second. And so to find the mass, which is what we're interested in doing here, we need to solve for m, and m is going to be equal to force times g, or divided by. And the force is the weight. Yeah. No. Yeah, because we're in this foot pounds place. So what is this? Divided by 8, 3/4. So your mass is going to be 3/4. So that's one part. And remember, the only other thing we need is k. That's the omega is going to be the square root of k over m. So we need k. And the stretch, the spring that where it stretches 4 inches is going to give us, by Hooke's law, it's going to give us our k, constant k. And so how do we find that? We said that Hooke's law says, what is it? Force is equal to k times s, the distance that it stretches. Is that right? And then, oh wait, better check. Is it right? Can somebody just say yes? Yeah, ks. So force is equal to k times s, and we know that with 23 or 24 pounds, this got stretched how many inches? 4 inches. And again, we want to change this into feet because we want to measure things in foot pounds. So we have 24 is equal to k times, this would be 4 divided by 12, right? 1/3. And so k is equal to 72. Okay. So if we have these two pieces of information, we can put it together. We can write it a couple of different ways. We can write it with m x double prime plus k x is equal to 0. So that would be 3/4 x double prime plus 72x is equal to 0. And then as we solve for this, we'll pick up what omega is equal to. So we have that, and we have x of 0 is equal to 3 inches is 1/4 of a foot, and x prime of 0 is equal to 0. So here's our initial value problem. Uh, 3 inches. All right. So now let's go ahead and solve for this. Probably want to divide out by 3/4. So we have x double prime is equal to or plus 72 divided by 3. That's 24, and then multiply it by 4, 96. And then if we solve for this, this is a differential equation that we've seen before, right? M squared plus, I don't know if M is a good letter to use. It looks like mass, but it's from the characteristic R. Capital M. I don't know. Just do M. So M is equal to plus and minus the square root of 96. And then because when you bring it over to the other side, it's a negative. So we have that I business that comes out. So anyways, your solution here is going to be x1 is going to equal to cosine square root of 96. I guess we have to use t. What? So we can pull out a 4. And how many? 4 root 6. So 4 root 6, and then your independent variable is t. This x prime is actually dx dt, or x double prime is d2x dt squared. And then your second one is going to be sine 4 squared of 6. So 4 squared of 6, by the way, is your omega. If you square that, you get 96, and then that's how we get. That's why they use omega squared, so that the omega is actually identified. And so we have your general solution, y is equal to c1 cosine 4 root 6t c2. Yeah, this is set equal to 0. So the external force happens when there's a machine that's running this spring system, which we'll get to hopefully by the end of today. Say it again? Oh, x is equal to. Gotten so used to putting y's. Or maybe we should do one better and just call it x of t, function of t. All right, so we're not quite done yet because we have initial conditions. And so let's throw in our initial conditions. We need to take the derivative and then put 0 in. So let's put 0 in here now. X of 0 is equal to, cosine of 0 is 1, and sine of 0 is 0. And so according to our initial condition, x of 0 is equal to negative 1/4, right? We need to take the derivative, x prime of t, taking the derivative of cosine is negative sine, and then you get this extra 4√6 coming out. And then the same thing, derivative is cosine. Derivative of sine is positive cosine with the extra 4√6 coming out. And then we'll put 0 in there. Sine of 0 is 0, so that goes away. And the cosine of 0 gives us a 4√6 c1 times 1. And this is supposed to be equal to 0 according to the initial conditions. So we have c1 is equal to negative 1/4, and c2 is equal to, this is c2, equal to 0. Oh, the negative 3 got, it was in inches, and it got transferred into feet, because we have to use feet and pounds. All right, so we have our final answer is x of t is equal to negative 1/4 cosine 4√6 times t plus 0. So this is all we have. Okay. Yeah, so this is the position of the spring at any time. And so if they ask you more questions like when is the spring going to have the highest point or the lowest point, you can just plug in or set them equal to or whatever. Okay. Any other questions? No, good thing I started a new page. Took up a whole page. All right, let's try one in the metric system. You guys were all excited about the metric system. So here says the force of 400 newtons stretches a spring 2 meters. A mass of 50 kilograms is attached to the end of the spring, and it's initially released from equilibrium position with an upward velocity of 10 meters per second. Find the equation of motion. So mhm. So if positive is going down, upward velocity means we're pushing it upward. So it would be a negative direction. So it's released from, so this is the stuff that would help us find our initial conditions. And it's usually a good place to start in case you don't know where to start. So it's released from equilibrium position. What does that tell us about the initial position? So it should be 0, right? Because it's released from the equilibrium. And then it gives an upward velocity. So velocity you should relate to the first derivative. And what's that? So it's negative because it's going up 10 meters per second. So now we're in metric system. So newtons is kilograms per or kilograms times meters or something like that. So we know that we're dealing with meters and kilograms. So if anything here turns out to be grams or centimeters or something like that, make sure you use the proper adjustments unless you use the centimeter gram equivalent. What is it, a dyne or something? Yeah. You mean which system to use, metric or otherwise? I think you should just go by what the problem has. I'm not going to expect you to convert from feet to meters and vice versa. So whatever you're given, you should just use that system. Yeah. All right. So force of so our mass is 50 kilograms. That's probably going to be m. So m is equal to 50. And then here, the spring stretching 2 meters is going to give us some information about our K, the spring constant. So again, force is equal to Ks. And then your force with 400-meter force, K times, and then this thing stretched down by 2. So K is equal to what? So we got M and we got K, and then we have the initial condition. So we set up our differential equation. 50 x double prime plus 200 x is equal to 0. Okay. If you have no damping, and since this is always going to be the format, we could just figure out what omega is, right? What's omega equal to? So that's omega squared, right? And then just take the square root of that as omega. Does that turn out to be a nice number? Isn't it like 2 or something? So then we know what the answer is, right? So x of t is equal to c1 cosine 2t plus c2 sine 2t. A few steps. Oh, if it's right, I'd take it. I mean, look at what happened in the previous example. Um, we have 96, right? And then this is the square root of 96. Oh yeah, that's why they want to call it omega squared from the beginning. Is that for this thing over here, this thing, because this is a plus, omega squared is positive and x is positive. When you bring that over, when you solve for the equation, it's always going to be an imaginary number. And so your solution here is always going to be C1 cosine omega t plus C2 sine omega t. So we could do, 3 or 4 of these problems till you see a pattern, or you just, I could tell you and then you can do it on your own to convince yourself that that's actually true. So here we are with the solution right away. And then we have our initial conditions, so we just put in our initial conditions to figure out the rest of the problem. So basically, your problem's done. I mean, you know, this is stuff that we've been doing already. Let's do it anyways. Um, we have x of 0 is equal to 0, x prime of 0 is equal to negative 10, and everything is in meters and kilograms and stuff like that, so we don't need to change any of these numbers. And we go ahead and plug those values in. So we take the derivative, um, x prime of t is equal to minus 2 c1 sine 2t plus 2 c2 cosine 2t. And we put in the initial conditions when x is equal to when t is equal to 0, then this is c1 plus 0 is equal to 0. So c1 is equal to 0 in this case. And then here for the first derivative, we put 0 in for t, and then we have 0 for the first one plus 2c2 times 1 is equal to negative 10. So c2 is equal to minus 5. So minus. So that's your answer. Okay, good. Move on. What? Now let's do some damping. There's damping and no damping, and then there's either damping or no damping with an external force. So that's a non-homogeneous. Yeah. The what? Yeah, we're not doing circuits. All right. So the damping force usually is described as something being proportional to the velocity. And so the damping force is usually just described as some constant times, well, the velocity, the dx dt. And so that doesn't touch anything with the acceleration term. It doesn't touch anything with the position term. And so the only thing we need to do is add on our velocity term. And so we see this this thing that they have here. So it turns out to be x double prime plus some constant times x prime plus another constant times x. And so that constant times x, we've known that from the previous page as being omega or omega squared. And so here they just introduce another variable, lambda, to help us describe the constant of proportionality to the to the velocity. And the way they would usually describe it is just saying it's proportional to the instantaneous velocity. And then they would say it's twice the instantaneous velocity or 5 times instantaneous velocity or whatever. And so that's really just a number that we have to put in. But then they have this 2 lambda as a number here. So what's 2 lambda equal to? What? 2 what? Well, anyways, beta. Well, in any case, this is they wrote it as 2 lambda because remember when we solve for these differential equations, we're interested to know what happens. We assume that your solution is going to be e to the some power, right? And then we figure out the coefficient of that power as being the solution to our auxiliary equation. So if we write this as our auxiliary equation, we have m squared plus 2 lambda m plus omega squared is equal to 0. And then we figure out what happens to this particular differential equation by figuring out what happens to the solution to this quadratic equation. And so the solution to this quadratic equation is dependent on what happens in the discriminant, the square root of b squared minus 4ac. And if we take a look at that, it's, if it's positive, then we have 2 real roots. If it's 0, then we have 1 repeated root. If it's negative, we have 2 complex roots. So if we, well, let me write it out first. M is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then if we just focus on what's inside, then what's inside is going to be telling of how our system is going to look like. So I guess what they do further here, before they do some analysis, is they look at 4 lambda squared minus 4 omega squared and just factor out a 4. So depending on what happens to lambda squared minus omega squared, we're having different cases. So if the discriminant is positive, then we have 2 real roots. If we have 2 real roots, your equation would be just the exponential functions without sine or cosine. And they call that overdamped. So these exponential functions will dampen your system right away. If the discriminant is equal to 0, then we have 2 real roots, and the 2 real roots will have e to the whatever, e to the m, or in this case it would be negative lambda t plus, or the other solution would be t times e to the negative lambda t. So that's a case where you have repeated roots. And then the last case is that when you have imaginary roots, you involve your sine and cosine. Okay, so these symbols over here, memorizing the solution for the first one where you just have the basic oscillating function, that's probably not too hard to memorize. But trying to memorize these solutions might be a little bit more difficult unless you've actually tried it out and used it a bunch of times. So in these problems where you don't have, what do they call it, free oscillating motion? Harmonic motion. And these examples where you don't have a regular harmonic motion, where you have this damping feature in your differential equation, then you might be interested in walking through the whole problem by finding your roots and stuff. All right, so let's try a problem. So I have 2 problems. One is using pounds. The other one is using the metric system. Let's just do one. Which one do you guys want to do? Metric system. So this has two parts. Let's just do one part because I don't think we need to do two parts. All right. Oh, come on. Copy. So we'll cut it and just do one of them. So 1 kilogram mass is attached to a spring whose constant is 16 newtons per meters. And so they gave us the spring constant already. Let's take that so we don't have to solve for K. So K is equal to 16. Then it's submerged in a liquid that imparts a damping force numerically equal to 10 times instantaneous velocity. So we get a coefficient for x prime now. And then determine the equation. So we got a 1 kilogram mass, m is equal to 1, and k is equal to 16, and then our damping constant, our damping force is numerically equal to 10 times the instantaneous velocity. We've been doing the initial conditions first, so might as well do that first. The initial conditions come here in part A. Part B is a different set of initial conditions that we're not going to do. So here the mass is initially released from rest at a point 1 meter below the equilibrium. So I need to figure out what x of 0 is and x prime of 0. And based on that sentence, I should be able to figure out both. So what is x of 0 equal to? -1? What? +1. All right, below is positive, above is negative. And x prime is what? 0 because it was released from rest. It just let go. So there's no push or pull to have an initial velocity. So here's our initial conditions. We're good with that. Now let's take our information here and see if we can come up with our differential equation. So 1 kilogram mass is attached to a spring whose constant is 16, and the damping force is numerically equal to 10 times um, the instantaneous velocity. What would be 0? What? What would be 0? Well, it says numerically equal to 10 times the instantaneous velocity, so I don't think that would be 0. I think it would be 10 times dx dt. And so it's a force that they're measuring it as a force, so we could just add that as part of our differential equation. So then we have 1 times x double prime, and here's our damping force, 10 x prime, and then here's our constant k, our spring constant, and that's equal to 0. Yeah. It'll be positive 10 because I said so. Um, so the damping force, if we look at it as a force, is usually slowing down, and so the force is negative. But that's when you're setting it equal to a force. But then when you bring it over to the other side, it becomes positive. Okay, so we have our differential equation, and it's a second order linear constant coefficients, and so we solve for it the way we've been solving for our differential equations that are not Cauchy-Euler. So we just find the auxiliary or characteristic equation and then solve for that. So we have m squared plus 10m plus 16 equal to 0. And can we factor this easily? Yeah, 2 and 8. Okay, good. So m is equal to, they're both positive, right? Oh, just get the solutions here. M is equal to positive 2 and positive 8. So we have these two solutions. We have, negative, both negative. And so we have distinct real roots, and that would put us in case one where it's an overdamped system. So this is probably not going to be, this is probably going to be pretty boring because it'll just, once you let it go, it'll just stop automatically. It looks like it stops, but infinitesimally small oscillations. And so your solutions here would be x of t is equal to c1 e to the negative. I'm going to go with a smaller number first. Doesn't matter which one's which. So here are our fundamental solutions put together into the general solution. Did I do something wrong? Oh. So lambda is what? It'll it'll work out. So lambda is 5 and omega is 16. What? So lambda is 5 um, plus the square root of 25 minus 16, and then minus also, right? So this is minus 5 plus 3. That's negative 2, right? And then minus 5 minus 3, that's negative 8. So it's, you see this the same? Yeah, so this thing needs to get distributed. So you get C1 e to the minus lambda plus square root of lambda squared minus omega squared, and then C2 e to the minus lambda minus square root of lambda squared minus omega squared. And so one of them was negative 8, one of them was negative 2. I mean, when you multiply, you add the powers, right? And you can factor the t's out, but those are the coefficients. Yeah, so this is I mean, if you can make sense of this, again, if you can make sense of this formula, then you're free to use it. But negotiating your lambdas and your omegas might be more difficult than it's worth, especially since we already know how to kind of do it a certain way. And these numbers over here will end up being the powers that you have. But again, that's if you want to really study the algebra behind it, it's really all just algebra, putting the and then using the formula. All right, let's use our initial conditions. That's x of 0 is equal to 1, x prime of 0 is equal to 0. So we need a derivative. So this is minus 8c1 e to the negative 8t minus 2c2 e to the negative 2t. And so we'll use our initial conditions when our function itself is equal to 0. We want it to be 1. So C1 plus C2 equals 1. When your derivative is equal to 0, we want it to be 0. Negative 8C1 minus 2C2 is equal to 0. So that's putting t is equal to 0 in there, right? You get two equations and two unknowns, and you just go at it, solve for it any way you want. Kramer's rule, addition rule, or whatever, whatever it's called. I suppose we should finish it. So I would probably just multiply the first one by positive 2, I think. 2c1 plus 2c2 is equal to 2. Add that to the next one. 8c1 minus 2c2 is equal to 0. And that would go away. We have negative 6c1 is equal to 2. C1 is equal to negative 1/3. And then C2, if this is equal to negative 1/3, then C2 is probably equal to positive 4/3. And then that's your solution. X of t is equal to negative 1/3 e to the minus 8t plus C2, 4/3 e to the negative 2t. So imagine this in a big heavy liquid, and then the mass is submerged in the liquid, and you do the initial condition, whatever, and you let it go, and then it just maybe moves up a little bit, and then the liquid kind of just holds it there, and just so that's probably what happens, and that's a case where it's overdamped. Okay, good. Questions? Yeah. Yeah, we're only going to do springs. Well, there's two cases so far. It's the case where it's not damped, and then there's a case where it is damped, and then this case has 3 cases. And then there's the catch-all where it could be either no damping or some damping, but it has an external force. And then so that's the last thing that we're going to do in 10 minutes. What? Yeah, let's do it. Are you talking about this? What? Of this? Always. Don't I always post a solution if I don't finish it? Okay. So we have external force. We go back to our force equation and just, we have the spring constant and the disposition from Hooke's law, and then we added on a damping factor, and then now we're going to throw in an external force, a function that's like a machine that's running the spring as it's doing whatever it is it's trying to do. And so if we put that into this equation, we have this external force, and it's essentially stuff that we've been solving for, except, so this would be the non-homogeneous differential equation that we've been solving for. And then it says here, recall that solution is a sum of the complementary solution and a particular solution. The complementary solution is known as the transient term, and a particular solution is called the steady state term. And so the steady state term is that this F is controlling it, and that's going to be the particular solution that we're going to solve for. And what happens in the long run is that um, this external force is pretty much going to control what's happening to the system in the long run. All right, let's take a look at an example that we're going to do in 7 minutes. Are we doing feet or meters? We're doing meters. Oh, I need to do this on a new page. So we have a mass 2 kilograms attached to a spring constant. They give us a spring constant. That's nice. It comes to an equilibrium position. Um, so it doesn't look like it has a damping factor. Yay. Starting at t is equal to 0, a force equal to this thing is applied to the system. Find the equation of motion. No damping. Okay? But there's an external force. So 2 kilogram mass. So m is equal to 2. Our spring constant k is equal to 32. If you want to jump to omega, omega is what? 32 over 2 is 16. That's omega squared. Omega is 4. We're halfway there. X of t. So we call this the complementary solution. C1 cosine 4t plus C2 sine 4t. Yeah, that's it. We're done. No, we're not done. Um, we also missed out on. Well, I suppose we should write our differential equation here. Yeah. So x double prime or 2x double prime. I guess we can bring. What was omega squared again? Yeah, 16. X is equal to 68 e to the negative 2t cosine 4t. Oh no. All right, I suppose we should also figure out our initial conditions. We can solve for initial conditions, by the way, without the x's here. Where are we? Uh, so the force attached to a spring, so x of 0 is equal to 0, x prime 0 is equal to 0. Okay, we're starting from rest, and then we're not pushing it or anything like that. We're letting this whole thing be controlled by this external force. All right, so we're here now. We can use this is I don't know. We can't separate this. Not the answer. I don't know what the answer is. So how would I do this? I think is this one of those things that we can use undetermined coefficients? This one, right? Wow. All right. Oh, what happened? So our y sub p should be equal to, uh, oh yeah. So I divided to, so this would be, uh, because that's how the problem should have started with the mass in front. And I kind of did this as if it was homogeneous. So this has to be divided by, so x double prime plus 16x is equal to 34. So anyways, to find your y sub p should be a e to the negative 2t, should be x sub p, doesn't matter, times cosine of 4t plus b e to the minus 2t sine 4t. Now, do we have to worry that this is linearly dependent with our, no, because why? No, that's not the reason. Because the right hand side is multiplied by e to the negative 2t, and so we don't need to worry about adding an extra t or anything like that. So take the derivative, take the second derivative, plug it back in, and solve for a and b. And that's it. You're done. All right, so hopefully there'll be a solution to this online somewhere, sometime. Oh, your review is online. Did you guys see? Okay, so we'll review tomorrow or next time.